So the focus of this next session is going to be on configuration management and telemetry. And for that, we'll be talking about Yang, openconfig, and gnmi. So just a quick overview. We're first going to talk about Yang, which is a configuration modeling language, which has been around for a while, originally used for netconf. We'll talk about openconfig, which is a set of configuration and telemetry model instances, so implemented in Yang and a few other things. We'll also talk about gnmi, which is the gRPC Network Management Interface used for runtime configuration and monitoring, and gNOI, gRPC Network Operations Interface used for runtime operations. So let's start with Yang. Yang is a data modeling language used for network configuration. It's used to express the structure of data, not the data itself. Instances of data is going to be in something like XML, JSON, or protobuf. And an XML, JSON, or protobuf message is going to be considered valid, or it's going to adhere to the Yang model if it follows the same schema that the Yang model defines. So Yang is a schema definition language, and then we have instances in XML, JSON, or protobuf. So from the Yang model, we care about really two things. One is the data tree organization. What's the structure of the data? This is where we have a bunch of nodes that have children. Eventually, we get to leaves, and each leaf is going to have a data type. We also care about the semantics of the leaves. These we get from the field description, and they're usually in English. So we have the tree organization we can largely determine or generate programmatically, and then the semantics we get from the textual description. A little bit of history. So Yang was originally designed as a data modeling language for netconf, if you've used that in the past. It borrows a lot of the syntax from SMI-NG. Yang is yet another next generation, and SMI-NG is SMI next generation, which is an evolution of SMI, which is the data modeling for SNMP, which is used to describe MIBs. So a lot of this is kind of building on work that the networking industry has been doing for years. So let's take a look at what Yang syntax look like. And we'll do this through kind of exploring a lot of the key features that you'll find in a Yang model. So the first thing is a module. A module is a self-contained set of nodes. This is the unit of compilation. So you have a module that you're going to compile. You have other pieces that are part of it. They're going to be not necessarily compilable units, but together when we have a module, we have a compilable unit. A module is going to contain some boilerplate, things like the Yang version that was used, a namespace, a prefix used in case it is imported somewhere else, a description, and a revision history. It's also going to have a bunch of other stuff that's going to define the rest of the structure. In Yang, we have a number of types. There's a bunch of built-in types, the standard binary bits, booleans, int types, uint types, strings. These are common to most programming languages. If you're interested in kind of the whole list, there's an RFC that defines this for Yang 1.0 and 1.1. But there's also a way that we can define new types. The first is identities. So identities are kind of an abstract, untyped, globally unique specifier that means something in the context of networking. So for example, we can have a speed identity, which is our base type for port speeds. And then we can also have instances of that, like speed 10G, which means this is a 10G port. So the semantics of these identities, again, are going to be described in text, usually English. And these can be used throughout our models that we have. The other thing that you can do is you can do something called creating a derived type. So a derived type is going to be basically a constrained built-in type. So here we have a uint 16 that we want to constrain in some way. In this case, we're going to constrain it to only the values 1 through 32. And this is called a port number. These types of constraints are also defined in the RFC if you're curious how you can constrain types. Next, we have groupings. So groupings are going to be reusable sets of nodes. So these are going to be things like containers or leaves that are going to be included in other containers. So a grouping in itself doesn't actually have any nodes in the module, but rather it's going to be describing like a subset of functionality we're going to inject into the model. So in most configuration models, we care about two things. How do we configure the device, and how do we read state from the device? And so typically, in openconfig and other modeling schemas, we have a grouping around configuration. In this case, we define a port speed that can be set for this given device. And this leaf has type identity ref. And it tells you that this is how you configure the speed of the switch port. And then on state, we want to read the status. This description's wrong, but we want to read the status. Is the port up or down? This is just seeing leaf in two different types of configuration. The way that we pull our overall hierarchy together is using something called a container. So a container is a node in our hierarchy that can have sets of children, and those children are going to have our leaves. So in this case, we're defining our top level or root container for our module called ports. Ports is going to have a list of port instances, and then the port instances are going to have a key. That's how we're going to identify them in our schema. And that key is going to be a port number. So we have a leaf port number, which is the front panel of our switch in this case. And then we're going to include our two groupings. So we have a config subtree, which is going to use the port config that we just defined. And then we're going to have a state subtree, which is going to use our port state grouping. You can see that in this case, we have something called config false here. So data in Yang by default is read-write, meaning the client or the controller can make changes to anything it wants. Data that's marked config false means that this data is read-only, meaning the device is going to populate this information, but the controller can't set it. This is what, things like, is the port up or down operationally? What are the stats on a given port? These are going to be the read-only portions of our tree. So for a complete set of kind of other terminology, you can see the RFC. And if you want to see a complete example all put together of a simple Yang model, this demo port Yang model, it's actually going to be part of our tutorial. You'll get some exposure to that in our exercise later. There's a few other things I wanted to point out about Yang. So we are looking at a single module in this particular example. But one of the powerful things about Yang is that you can actually import modules into other modules. So we can take a port module and include it in sort of an overall device schema. And for that, we use the import statement. So we can include types, groupings, or other models in other modules. We can also augment a previously defined schema with additional attributes using an augment statement. And then if a device doesn't support a particular part of a Yang schema, it can define a deviation. So augmentation is how a vendor can add to a common model, and a deviation is how a vendor could say, I don't adhere to this common model in the way that you expect. So just taking, once you have your model defined, kind of how do we go from the model to other representations? So we start with your model, like the demo port model we were just looking at. And from that, we can generate a Yang data schema. So DSDL is an example of an XML schema, or maybe you're familiar with XSD. These are programmatic descriptions of how a schema should look and what the constraints on that schema are. So we get a schema from our Yang compiler. And then using that schema, we can also generate data that adheres to the schema. So in this case, from a DSDL description or an XSD description, we can generate XML code that adheres to our Yang model. Like I said before, Yang was written for netconf, and XML was the canonical representation for Yang initially. And it's still the canonical representation for netconf, the protocol. So if you want to start configuring or passing data between a controller and a device, you need a protocol to do that, and netconf is a valid protocol that is built around accepting models that are Yang-based. So netconf itself doesn't have any Yang built into it, but rather models that you've written that are represented or encoded in XML can be passed over netconf. We can also do this with JSON. So there's a JSON schema that can be generated from a Yang model. We can generate valid JSON that adheres to that schema. And then RESTconf is an example of a protocol that's been used to read and write Yang structured data over HTTP. So you can also map between the DSDL and JSON schema or XML and JSON. And there's been tools that people have written that enable you to do that. The new kid on the block, so to speak, with respect to data schema for Yang is protobuf. So there's now a compiler called YGOT that you can use to generate protocol buffer definitions or protocol buffer messages based on your Yang model. From that, we can use either the textual or binary representation of those protobuf messages. And this is the canonical representation that we use in gnmi, which is our gRPC-based configuration API. It's also worth noting that gnmi supports a JSON encoding. It doesn't go so far as to accept XML by default out of the box, but you could hack XML into if you really wanted to. Yeah, question?
So for this generation, it doesn't generate the services, right?
Correct. So the generation we're talking about here is just the hierarchical messages, the data structure of the messages that's going to be passed between. The service is going to be gnmi. So gnmi is our service that has a get, a set, subscribe definitions. And then the messages you're going to pass to those services are going to be the protobuf encoded messages that adhere to the Yang schema. Does that answer your question?
Yeah.
Okay. The other thing to mention is that there is a canonical transformation between protobuf and JSON, and also protobuf and JSON schema. So these formats are largely interchangeable, and there are tools that people have written to move between them. So just because your stack originally was built on netconf and XML, there are kind of migration paths if you didn't want to rebuild everything from scratch. So the next thing I want to talk about is what does a workflow look like for someone that wants to build a client or server? So you start with a Yang model, just like we did before, and we run it through a Yang compiler. And we can also generate language-specific objects, enums, and validation code. So for example, there's Yang compilers for Go, for C++, for Java, for Python. And these languages are basically going to take the Yang models and generate either Python classes, Go structs, C++ classes that are going to adhere to the Yang model, as well as provide some validation to make sure that the types are of the right format. So this is kind of a good basis for someone that's trying to build a client or server, is start with the Yang compiled objects in your native language. And then take the textual descriptions, like what is the meaning of each of these fields, and write your code. That code that you write is going to go through a regular compiler like Go, GCC, Java C, whatever. And it's going to produce a client and a server. And so that client or server is going to understand the schema of the objects that we're using, but we still need to communicate between them. And so for that, we have a runtime API. This is a model-independent API, for example, netconf or gnmi. And on the wire, the messages are going to be encoded using protobuf, JSON, or XML. But the clients can then translate those on-the-wire encodings into native objects that they use. It's also worth noting you could just take the protobuf representation and generate native objects. So you could have protobuf-based objects, or you can have native Yang objects. The advantage of the native Yang objects being primarily schema validation. And the other thing to note is that clients and servers can be written in different languages. So you could have a Python client talking to a C++ server. You could have a Java client talking to a Go server. It's really mix and match because our on-the-wire and our runtime API are program language independent. So next, before we go on to that, any questions about Yang, Yang schemas, anything? OK. So the next thing we'll talk about is openconfig. So openconfig, it's an organization. They have got a variety of network operators and network operators use cases that they've considered. And the goal here is to develop vendor-neutral data models for configuration and management that are supported natively by network hardware and software devices. So rather than having every vendor and every operator define their own models to solve the same problems, let's look at common use cases and define models that solve these problems in common ways. Another goal is to develop modern and efficient transport protocols for network configuration, telemetry, and operations. So gnmi and gNOI come from the openconfig working groups. There's currently a whole pile of models hosted on GitHub. And this is kind of a representation of the models. We have a top-level device, which has networking, routing, BFD, interfaces, platform, system, QoS, et cetera. All kind of networking use cases, both traditional networking and SDN are kind of covered under this openconfig umbrella. So Stratum today uses openconfig as the baseline for our configuration and telemetry models. However, many of these models aren't really relevant to an SDN data plane. So for example, like MPLS configuration, OSPF configuration, or BGP configuration would be more suitable models for our control plane and not our data plane device. So the models we're interested in are primarily interfaces, LACP, VLANs, platform, QoS, and system. These are going to be kind of more of the hardware-focused configuration. And there's also some augmentations that we have. We've added some additional things that we're working on getting pushed into the openconfig standard, but for now they're additions to it. And vendors, if they want, can also provide augmentations or deviations on top of this for their own implementations on Stratum for their boxes.
Question.
Yes?
Why is VLANs on this?
It's a good question, and it has to do with how you define your network model. So some users of SDN define their network model starting at L3, and they still use LACP and VLANs to do basic Ethernet trunking, basically trunking configuration. Other users push that into their SDN controller.
Yeah.
So it's basically, do you consider basic L2, do you want trunk ports as part of your network model that's provided, or do you want trunk ports to be implementation that the SDN controller pushes? A pure SDN solution would exclude LACP and VLANs, as you mentioned. So just to make things a little bit more concrete, I took a look at the openconfig-interfaces.yang model. And this model is like hundreds of lines long. But there's a cool tool that we'll use later in the tutorial called pyang, which is a Python-based Yang compiler that can produce, it's kind of a framework. We'll get into the details later. But using this, we can generate a tree representation. So we see our top-level module is openconfig-interfaces. We have our root node, which has a list of interfaces. So this is kind of a more complicated version of the demo port we just looked at, with a config block and a state block. You can see in the config block, we have things like enabled and type. And in the state block, openconfig convention is to include all of your config as part of state, and then also to include things like the operational status, as well as counters, like ingress counters and egress counters on ports. Question?
Sorry, I have a very basic question. Why some of them have a question?
Oh, so a question mark means I believe it means the field is optional. And then RW is, this field is read-write, and RO is read-only. And then you can see that the key here is encoded in the brackets for the list. So it's more of a map in traditional data structures terminology than a list, or a dictionary than a list, because we have a key that then maps to a value. Also, in this case, this is an example of a leaf ref, which is a more complicated structure. Basically, this is like a virtual field that's actually backed by something in the config part of the tree. Any other questions on openconfig before we move on? OK. So next, we'll talk about gNMI, gRPC Network Management Interface. So gNMI is a generic API used to read and write config state. It's suitable for any tree-based data model, So Yang is an example of a possible data model, and it's the canonical one that we use, but you could use something else. You can also view it as a successor to netconf or restconf. And some of the big advantages that we've seen here is that from a serialization perspective, we're moving from XML, which is a fairly verbose human-readable text format, to a compact binary representation. We've upgraded the transport from SSH to gRPC, where we can more easily have multiple parallel operations happening, as well as an ability to do server push. We have the option to be diff-oriented. So in netconf and restconf, typically you return an entire subtree in response to a GET request or a GET. And in gnmi, we have the option to only return elements that have changed. So in addition to being more compact on the wire, we can also send less data, like fewer fields. And then we also natively support telemetry. So both restconf and netconf have kind of out-of-band mechanisms to push from the server to the client, but we do this out of the box in gnmi. So as we mentioned before, gnmi is a gRPC service that provides an ability to retrieve device capabilities. So what models do you support? This is similar to netconf. We can also read and write configuration using get and set. And then we can subscribe to streaming telemetry updates. So we have 4 RPCs, capabilities, get, set, and subscribe, that each have messages. And you can see that subscribe has an ability to stream bidirectionally. The rest are going to be more traditional RPCs. If you're interested in the protobuf definition, it's on GitHub. And the whole specification of gnmi, English language specification document, is also available online. So let's take a look at what a get response looks like. It's a little bit more interesting than the get request. So we made a request for a given Yang path, or Yang-defined path, and we're going to get back a get response. In that get response, we're going to get a list of notifications. And notifications are a message type that includes a timestamp. When was this notification generated? A prefix. So if you want to prefix the entire path for your notification, as well as a set of updates. So an update is going to be a path, a typed value, and whether that this is duplicates or not. But the interesting thing here is path and typed value. So if we boil this down, the response is going to be a list of notifications, which has a list of updates, which are going to be path, typed value pairs. So yeah, just to focus on the update again, these are batches of configuration that can be written or read. They have 2 parts, a relative path to the prefix that was specified, as well as a value. And then updates can either transmit configuration snapshots. So you can either pass a tree or subtree in its protobuf or JSON encoding, or you can pass leaf-only values as path value entries. And we'll see examples of both in just a second. It's also worth noting that get, set, and subscribe all use the same messages to send or receive data. So updates is how we either set new configuration or retrieve configuration from the device. Yes, question?
Is subscribe like a trap?
Similar to, yeah. Similar to a trap in SMP. So taking a look at the update definition, path is going to be a set of a path representation that encodes the tree or the leaf value or subtree value in Yang. And the typed value for snapshots is either going to be a protobuf any, a JSON value, arbitrary ASCII text. This is where you could hack in your XML if you wanted to. And then a more compact representation of protobuf any. So protobuf any and bytes are both used for encoding protobuf data. JSON can either use regular JSON or RFC 7951 JSON. And then ASCII could be used for out-of-band agreements between your 2 devices. So let's look at an example. So if we made a request, say, for interfaces interface 1.0, a notification that could be sent by a server, and again, this is the text representation. This would be actually encoded in binary on the wire, would be an update with a path interfaces interface name 1.0. So this is the path portion. And then we can use any val, and we could say that this is of type openconfig-interface. And then the value of that openconfig-interface is going to be a message defined by our WYGOT compiler that's going to have things like enabled, port speed, and maybe the interface index. Just for your information, Stratum today only supports returning snapshots for GET requests on the root path. But we could extend it so that it could also provide snapshots of subtrees as well. So this is basically a way of getting, this is a snapshot encoding of the data at a particular node in our tree. So let's talk about subscribes. So gets are pretty easy. You request a path, you get back a path and a set of values. For subscribes, the client is going to submit a subscription list containing a path that they're interested in, subscription type. So those types are target defined, meaning when you want to, send me an update. On change, which means if there's a change in value, like port up to port down, send me an update, or sampling. And sampling means periodically I want you to send me updates. There's also a subscription mode. The first one is once. That's basically a get. Send me the data once, and then you can close this subscription. Streaming. So streaming means we're using target-defined on-change or sampling. It means I want you, the server, to stream me updates when I've based on my subscription type. And then polling. Polling means I'm going to give you a set of paths that I'm interested in, and then I'm going to send you a poll message whenever I want the server to respond with the new values. So by default, when you establish a subscription, the server sends a snapshot of the current state for the requested subscriptions, unless you want to suppress it. But the default is send a snapshot first, and then servers will send updates per the subscription type and mode. So if we have an on-change subscription, if a port goes up or down, we'll get an update. This is where the sort of schema-less or diff-oriented approach really has an advantage. Because if a port goes up or down, instead of having to provide a whole snapshot of the interface, we can just provide a path to the leaf and a new value. So we're actually minimizing the amount of data we need to transmit, and also that the client needs to process. So in subscribe, typically we'll use this technique of just supplying the leaf nodes that have changed, rather than the whole configuration. So let's look at the other half of TypedValue. So we saw the snapshot values. These are the TypedValue attributes that are used for leaves. So we have strings, ints, bools, bytes, floats, and a scalar array. So these are kind of the simple types that can be leaves in our Yang models. And these ones are used for our sort of schema-less transmission. So let's look at an example of a subscribe for the same path, interfaces interface 1.0, using schema-less. So we have first, in this case, we're going to use prefix to say that all of the updates are going to be for interface name 1.0. And then our updates are going to be a path. So in this case, config enabled, and a value, true. Or a path, config port speed, and a value, speed 100G. Or a path, state IF index, and a value 128. So devices can elect to use schema-less mode when responding, and Stratum by default today does so for all non-root paths. And also if you want to get state information, it'll use this schema-less approach. This prefix optimization, being able to minimize the paths in repeated updates, is not something that Stratum does today, but is something that could be implemented as well. We could optimize a response so that we pull out the longest common path into a prefix and do this to minimize the data that we send. So let's look at set. This is the third of our operations. And clients can perform set in 3 types of set in a single request. The first is delete. So if you want to remove a node from a tree, we can provide a path to be deleted. If you want to completely overwrite a leaf node or subtree, you can replace it. And if you just want to update a node with some explicitly included values, you can use update. So the difference is if you had, say, a path that was missing in replace, then it would be implicitly deleted by a replace. Whereas if a path was missing in an update message, then we wouldn't make a change. We would leave the existing unmodified configuration as it was before. If you want more details on that, I suggest reading the gnmi spec. It goes into much greater detail of the behavior of those two. The last thing was capabilities. So this enables clients to ask a device for the device's gnmi version, the set of supported Yang models, supported encodings, and its extensions. So we'll get back a capability response that has a list of model data. Model data is basically name, organization, and version of the models that we're supporting. So for example, we have maybe openconfig-interfaces, openconfig platform. We support proto encoding, and this is gnmi version 070. So this is a way, when you're just getting started from a client, to interrogate a device to understand what types of models you can use to interact with it. A network device might just, have this kind of understanding that this data, like for example, whether the operational state of a port is up or down, is something that is only going to change if a network event happens. And so for that, it might be on change for that field. For something like counters, it's going to understand that every single byte that comes through your switch is going to be incrementing this counter, and it doesn't make sense to just destroy your client with thousands and thousands of updates a second. So for that, it might have like a default sampling interval, and it might sample those results back to the client. But yeah, target defined is basically enables you to kind of just trust the device to send you updates when they're relevant. And if you want to be more specific, you can either use on change or sampling for specific paths to get what you want. And then polling is basically a way of, if you have a long list of paths that you care about and you don't want to make GET requests every single time and be transmitting those GET requests, it's a way of just saying, this is overall the set of things I care about, and every time I send you a message, like a token, I want you to respond with all of the things I asked you about before.
Okay. So you don't have to ask again
For the whole list of paths, yeah. It's like, yeah, this is the list that I care about, and then I want to know, I want to know, I want to know. Yeah. Yep. Other questions? Okay. I'll also touch on gNOI. So gNOI, or gRPC Network Operations Interface, is actually a collection of services. You could consider these microservices that are for operations and runtime management. So for example, if you want to reboot a device, if you want to push or rotate SSL certs, if you want to do bit error rate testing or diagnostics on a port, if you want to do ping testing of the management plane, these types of operations have been modeled in gRPC, so you don't have to be sending commands to a bash shell and then p-expecting results. So each service contains multiple RPCs and is modeled in protobuf, and this allows also, gNOI also includes some control of legacy network protocols like MPLS or BGP or spanning tree, but those ones aren't as relevant in the Stratum case, but gNOI could still be used on top of traditional networking devices. Stratum initially is targeting cert, file, diag, and system services. And let's just take a quick example of one of these services. One thing I'll note about gNOI is that in netconf and Yang, there's this notion of RPC for defining methods that can be run on a device and a way to pass parameters and retrieve values. You can think of gNOI as kind of an evolution of Yang RPC. So could it be used to describe arbitrary? So each of the RPCs that we have is explicitly modeled in protobuf. So if you wanted to kind of have like a bypass or something where you had like a generic string or something you pass through to the shell, you could do that. We don't have one explicitly defined now. But new devices could introduce. Yeah. new devices could either add additional RPCs to the protobuf definition for a particular service, or they could introduce a new service. So for example, in system, we have ping, traceroute, time, set package, reboot. And then instead of passing a string of command line parameters, we have more semantically meaningful types that are going to be provided as inputs to those operations. So for example, we can pass a delay and a message rather than having to pass, the dash options in the reboot command in your normal CLI. So the next part we'll do is we'll get into the exercises. So just a quick overview. The goal of exercise 2 is to help you understand the Yang language. So we're going to look at a simple model, demo.port.yang, and a more complicated set of models, openconfig-yang models. And to do that, we're going to use Pyang, a Yang compiler framework, to help visualize the models using the tree representation we used in the slides. The second part of the exercise is to help understand Yang encoding. So we're going to use Pyang to generate the XML schema and a skeleton XML model or instance, as well as YGOT's proto-generator, which is another Yang compiler, to generate protobuf messages based on the models. And then finally, we're going to try to build an understanding for Yang-enabled transport protocols using gNMI by using a simple gNMI client called gnmi CLI to get, set, and subscribe to configuration from a running Stratum BMV2 switch. So the containers we'll be using for this exercise is first a Yang tools container, which we can start with make Yang tools. And this is where Pyang, proto-generator, openconfig models, and the binary decoder I was just alluding to are located. A second container is the Stratum MN container we used in the first exercise. This is where Stratum BMV2 is running. And it's only going to be for the third part. And then the last container is the gnmi CLI container, which you can start with util gnmi CLI. And this is also what we'll use to interrogate the device in part 3 of the exercise. So it's time to get to work. If you go to the ng-SDN directory, exercise 2, it has the instructions for this. If you've already done the pull in the first exercise, you shouldn't need to do that again. But yeah, we'll spend the next, I think, 30 minutes or so working on the exercises. And if you have any questions or need help, feel free to raise your hand, and someone will come try to help you out.